Weather. Our life depends on weather. Do I need to wash my favorite jumper? Can we go to the picnic today? Should I risk hanging the washing out to dry? We can easily check the weather forecast from our phones or any other electronic device. But how do our phones know? What really is the process behind predicting the weather? Well, this is when it gets a bit technical. Weather and natural disaster warnings is just one simple everyday example of what geostationary satellites can observe during their orbits. A geostationary satellite is an Earth-orbiting satellite placed at an altitude of approximately 35,800 kilometers directly over the equator, revolving in the same direction the Earth rotates, west to east. A geostationary satellite observes a specific point on the Earth constantly moving at the same speed as the Earth and taking approximately 24 hours, just like our Earth, to complete one full orbit. These types of satellites provide a successful platform for live broadcasting, telecommunications, and weather forecasting. A limitation of a geostationary satellite model is the fact that it orbits at a very high altitude, meaning it cannot observe minuscule details on Earth. This can only be done through a low Earth orbit. Since one geostationary satellite can only cover around 1/3 of the Earth's surface, around 2 or 3 need to be put into orbit for worldwide observations or worldwide broadcasting, increasing the expense of the satellite system. But before we go any further, let me address a common misconception faced by many people regarding geo-orbits and satellites. All geostationary satellites are geosynchronous, but not all geosynchronous satellites are geostationary. Tricky! This seems to be the origin of the misconceived notions. Clearly, there seems to be hardly any difference between the two. However, although countless similarities, there is one major difference between these two orbital properties. A geosynchronous satellite may or may not be following an inclined orbit in relation to the equatorial planes. This means the satellite can be on any inclination. A geostationary satellite, on the other hand, cannot be on any inclination other than 0, remaining exactly above the Earth's equator at all times. Alright, so now you know what a geostationary orbit really is. Let's go way back in time, pinpointing the exact person who introduced the notion of it. Henry Potočnik was the man who first introduced the notion of a geostationary space station or satellite with radio communications in 1928. Venus Equilateral was the first vague appearance of a geostationary orbit in popular literature, a story written by George O. Smith. Extraterrestrial relays. Can rocket stations really give worldwide radio coverage? British scientist, author Arthur C. Clarke published this article thoroughly discussing the workings of a geostationary orbit in 1954. Fast forward 9 hard-working years later, the first geostationary satellite, SYNCOM 3, was launched into orbit on the 19th of August in 1964. This satellite was then immediately put to use to telecast the 1964 Summer Olympics in Tokyo to the United States. Exactly 10 years later, in 1974, America's first domestic and commercially launched geostationary communications satellite was put into orbit by the Western Union and NASA. Now let's focus on the specific example of a geostationary satellite. America's GOES-13 satellite is used to predict weather patterns and issue natural disaster warnings. Stationary GOES-13 satellite, we're going to be using the equation radius cubed over time or period squared is equal to gravity times mass of the Earth over 4 pi squared. The radius of the Earth is 6.38 times 10 to the power of 6 plus the altitude, which is 35786 times 10 to the power of 3 cubed. The time is t squared, the unknown. The gravity is 6.67 times 10 to the power of minus 11 times the mass, which is 5.97 times 10 to the power of 24 over 4 pi squared. Then, using algebra, the person is left by 4 pi squared times 6.38 times 10 to the power of 6 plus 35786 times 10 to the power of 3 in brackets all cubed is equal to t squared times 6.67 times 10 to the power of 11 times the maths again, which is 5.97 times 10 to the power of 24. Next step is square rooting it to get the unknown, which is t. Square root 4 pi squared times 6.38 times 10 to the power of 6 plus 35786 times 10 to the power of 3 squared over 6.67 times 10 to the power of minus 11 times 5.97 times 10 to the power of 24. You're left with square root 7 for 32703096, which then equals 86213.12601 seconds divided by 3.6, which is equal to 1436.885433 minutes, divided by 3.6 again, which is equal to 23.95 hours. This proves that a geostationary satellite does indeed spend 24 hours, which is one whole Earth day, to complete one orbit. So now we're going to be calculating the orbital velocity of the GOES-13 satellite. Now there's two ways of calculating the orbital velocity, and the first way we're going to be using is V equals 2 pi r over t. V obviously standing for velocity, 2 pi, r standing for radius of the orbit, and t standing for time or the period. So we're going to start off by doing 2 times pi times 6.38 times 10 to the power of 6 plus our altitude or radius, which is 35786 times 10 to the power of 3, and put that all over 86213.1260 because that's obviously the time in seconds of our orbital period. Put that in the calculator and you will get 3073.04472. Now that is our answer in meters per second, but we want to put it into kilometers per hour. So what we're going to do is we are just going to times that by 3.6, getting the answer of 11062.96099 kilometers per hour per second. So the second equation we'll be using to figure out the orbital velocity, and we'll be cross-checking the answers of both, is g, which is gravity, mass, which is the mass of the Earth, divided by radius of the Earth plus altitude, and all of that square rooted. So V equals to square root 6.67 times 10 to the power of 11 times 5.97 times 10 to the power of 24, put that in brackets, all over 6.38 times 10 to the power of 6 plus 35786 times 10 to the power of 3, put that in brackets, and square root all of that. So what you're left with essentially is square root 3.98199 times 10 to the power of 14 over 42166,000. So the velocity in meters per second is 3073.04472. And then to get that into kilometers per hour, which is what you normally use in space, is 11062.96099 kilometers per hour. So obviously both velocities are approximately the same amount, meaning that the calculations were correct, and when they were cross-checked, it improved the reliability.